So unit one, of course, was just our working with arithmetic and our different forms of numbers. Unit two changes gears drastically, and we start talking about measurement. But not just about simple measurement. We're assuming you have all used a ruler and know a little bit about how to use a ruler. So we're assuming you're good with that. What we're going to be working on here in Unit 2 is some of the theory behind measurement, some of the history of measurement, and how to make sure that when you're writing measurements and reporting them, you're doing it in such a way that the person reading it understands it the way that you measured it. And so we look at measurement. Where did it come from? Well, measurement came from a need to communicate. If you and I are both trying to build a table that's, two of the same table. If we're in the same room, it's not a big deal. If you want to know how long the leg is, you just walk over and hold it next to mine, mark it off, whatever. I want to know how big the top of yours is. We go over, we trace them out. Not a big deal. But if you're down the street or across town, there needs to be some way to get that information to you. I mean, I suppose you could cut a string or a stick to those lengths and send them. But that's inefficient. It's nice to be able to sketch it out and label a drawing and have a whole bunch of sizes all at once. And so measurement is what we chose to do. Now, I might take this piece of paper. And let's say you are trying to make something the same size as this piece of paper. And so I might measure it out using my pen, and I might say it's 1, 2, it's just over 2 pens long. You probably can't see it really well, but my pen comes just short of, the second pen comes just short of the end of the paper. So I send that message to you. It's 2 pens long. So you take your pen, you go 1, 2, or you can see 2 goes past. 2 pens is longer than the sheet of paper. What was the difference? Well, our pens were, I hope if I hold the tips together, our pens were different sizes. You can see the one pen is a little bit longer than the other one. For measurement to work, there had to be 2 things that had to happen with the measuring device. Both people had to have one, and they have to be close, at least, really close to the same size. Now, in modern times, they're exactly the same size because we've standardized them. But at one point, it wasn't quite that well organized. They used objects that most people have, but they might have a slight variation from one to the next. We'll talk about those units a little bit later on in this section of the course about what did they actually use to measure. But once they actually chose that unit that they were going to use to measure, a lot of things happen. Eventually, they got to where they evolved a little bit so that they could measure a little bit faster. So rather than taking that object like I did with the pen and moving it from one spot to the next and counting, they developed a ruler. Basically just a stick that was marked off. Let's say we're using pens here. I'd make a mark right there, that's 1 pen. Mark right there, that's 2 pens. I might have a mark here for 3 pens. Now, the problem with this measuring system is not very precise. There's a lot of gaps here. I put this blue line in there. That blue line, when I go to measure it, I have to report it as being 2 pens long because it's closer to the 2. Well, you might say, well, it's kind of in the middle. Can't we say 2.5? If you say 2.5, that's implying to whoever reads that measurement that your measuring device went down to the half of a pen. We don't have that. This device doesn't do that. Or we might have the green line there. Again, that green line is closest to 2 So you'd have to report it as 2 pens long. Well, those two lines are not the same length, but this measuring device cannot distinguish between them. It's called precision, degree of precision. We can make this measuring device more precise by putting half marks in here. Now this device is capable of measuring to the half of a pen. Problem is, both the blue and the green are closest to 2.5 pens now. So they can cut each of those in half to make quarters. However, both the blue and the green are still closest to 2.25. So we keep cutting. Now we've cut it down to where the blue one is closest to the 2 3/8, the green one is closer to 2.5. We are finally precise enough to tell the difference between these two objects. That is referred to as a degree of precision. In a measuring device, the degree of precision is the smallest unit. So for this measuring device, that smallest unit is 1/8 of a pen. Now, it could be 1/8 of an inch, 1/8 of a whatever unit we're using. The technical definition of precision is the ability to distinguish between similar objects. This green line and blue line were close to the same size. And this measuring device here couldn't tell the difference between them until we got down to that 1/8 of a unit. So precision itself is the ability to distinguish between the two objects. The degree of precision is that smallest unit. This device is capable down to the 1/8 of a unit of distinguishing between two objects. You will notice, though, even though I'm listing the blue object here as 2 3/8 units, and the green object is 2.5, neither one of them are exactly on that piece. For the green line here, for example, it's not exactly on the 2.5. In fact, anything from here to here would have been called 2.5. So it doesn't have to be exactly on that division that we're measuring, it just has to be closest to it. Well, if we look at this, how far away from the 2.5 can that be? Well, it can be halfway to the next unit. That is called the maximum possible error, or just the possible error. I believe your textbook actually even just refers to it as the error. The possible error in a measurement is 1/2 of the degree of precision. So for this measuring device, it's 1/2 times 1/8, or a 1/16 of a unit. So what that means, anything measured on this device, any measurement reported is only precise or only accurate to within a 1/16 of a unit. A little more evenly spaced there. So we measure this object here. I'm going to label this 1 and 2. We're gonna just go with inches because that's what we're used to using as inches. In your notes, write down, first of all, what the measurement is. Second of all, what's the degree of precision of the measuring device? And what is that possible error in the measuring device? Well, my spacings here aren't very even, but you can tell by the markings that those are marked off to 1/4 of an inch. This is 1 1/4, 1 1/4, 1 1/2, 1 3/4, and it is closest to the 1 3/4 inch. So the measurement would be 1 3/4 inches. Excuse me. The degree of precision of this measuring device is the smallest division. Well, the smallest division here is 1/4 of an inch. The possible error, well, anything from here to here will be counted as 1 3/4. So halfway to the next division, the possible error is always 1/2 of the degree of precision. So 1/2 times 1/4 gives us a possible error of 1/8 of an inch. So what this does is it gives us a range. When I say that this object, this blue line, measures 1 3/4 of an inch on this measuring device, I'm not saying it's exactly 1 3/4 of an inch. Measurement is always approximate. In other words, it is always rounded. Measurement is to the nearest unit, not to an exact. I mean, it's always slightly between. So there's a range of possible measurement here from our measurement, the smallest it can be, or the minimum actual size, is the measurement, 1 3/4 inches, minus the error of 1/8 inch, which gives us a minimum size of 1 5/8 inches. The maximum actual size for that measurement would be the measurement, 1 3/4 inches, plus the possible error of 1/8 inch. That's 1 7/8 inches. So when I say that this object measures 1 3/4 inches on this measuring device, what I'm really saying is it is somewhere in the range of 1 5/8 inches to 1 7/8 inches. That's really all it is telling us. It's not telling us an exact number. Now, we're going to work more finding these ranges here over the next several minutes. But the big thing we need to be aware of when we do operations with measurements, we have to account for the fact that those measurements are not exact measurements. So looking at this measuring device, I want you to give me, for this blue line, measurement, and then we're going to call it the implied range of measurement. So what is the actual measurement you would report, and then what range is that measurement implying? So in your notes, go ahead and do that. We'll go over it here in about half a minute. Okay, so the first step you really have to figure out in any of these is what does each division on the ruler stand for? So between known markings, this is 1 inch and this is 2 inch. I should have said that we're going to assume this is inches again. Excuse me. We try to avoid going from 0 to 1 just because on many rulers the corner gets rounded off and the first marking might be missing or obscured a little bit. So we typically go up from like 1 inch to 2 inch. We have 1, 2, 3, 4, 5, 6, 7, 8 gaps. Now you should note I did count the gaps, not the markings. It's the spaces that matter. There are 8 spaces between 1 inch and 2 inch. So that means each space here is 1/8 of an inch. Because it takes 8 spaces to fill 1 inch. So now back to our measurement. This is 2. This would be 2 1/8. It would be 2 2/8 or 2 1/4. It is closest to the 2 1/4. So 2 1/4 inch. So that's our measurement. To do our implied range, we have to do some other things along the way. First, we need our degree of precision. Well, each space is 1/8 of an inch. That's our degree of precision, is 1/8 of an inch. Next, need the possible error. Well, the possible error here is 1/2 of an 1/8 inch, which is a 1/16 of an inch. Typically, we really should write that as plus or minus 1/16 of an inch is our error. Because whatever we measure could be up to a 1/16 smaller or a 1/16 larger. So then our range is 2 1/4 inches. Our measurement minus a 1/16 of an inch, which would be 2 3/16 of an inch. Up to our measurement of 2 1/4 inches plus our possible error of 1/16 of an inch. Hence the plus or minus. We added it here, subtracted it there. 2 1/4 plus 1/16 is 2 5/16 of an inch. So for this measuring device, when I say that blue line is 2 1/4 inches, what I am really saying is it's between 2 3/16 and 2 5/16 inches. Well, when we're using fractional measurement like this, the only way we know what the degree of precision is, and then of course what the error is from that, we must know the measuring device. We either have to have a picture of it or we have to be told what the degree of precision is. So we might have a measurement of 5 3/8 inches on a device with degree of precision of 1/16 of an inch. That's all we need to know then to find the possible range or potential range of that measurement. Because then, of course, the possible error will be that 1/16 of 1/2 of that 1/16 of an inch. So 1/2 times the 1/16 is 1/32. So plus and minus 1/32 of an inch is our possible error. So then our range will be our measurement, 5 3/8 inches minus a 32nd. That's 5 11/32 of an inch. To our measurement of 5 3/8 inches plus our error of a 32nd of an inch, which is 5 13/32 of an inch. So with fractional measurement, you must have some information of some knowledge of the measuring device. Either the measuring device itself so you can see and figure out the degree of precision, or you must be told what the degree of precision is on that device. Well, for you guys in machining, luckily a lot of your stuff is done in decimal measurement. Which makes life a little bit easier in some ways, but it's a lot more subtle. You have to really look for it and understand what you're looking at. For example, is there a difference between 8.2 inches and 8.20 inches? Most people would say, nah, it's the same thing. But mathematically, the numbers numerically, 8 and 8.2 mean exactly the same thing. But 8 or 8.2 and 8.20, I should say, mean exactly the same thing. That 0 on the end after the decimal doesn't add anything numerically to it. But technically, that 8.2 inches implies that we are working with a measuring device that only goes down to the 1/10 of an inch. And whatever it is we measured is somewhere between here and here. The 8.2 inches implies a degree of precision. I'm just going to write precision of 0.1 inches. Where did I get that? The degree of precision is the place value of the smallest digit, the last digit. Well, the last digit here is the 2 that is in the tenths place, the 0.1 place. That's your degree of precision. So that means the potential error here is plus or minus half of that is 0.05 inches, which is what that green line is showing. This is 0.5 to the left, 0.5 to the right. So that's giving us a range. 8 minus 0.05 is 8.15. 8.2 plus the 0.05 is 8.25. So that is the range being implied by that measurement when we report it as 8.2 inches. Well, the 8.20 is telling us something a little bit different. The 8.20 is telling us that we have a ruler that's capable of measuring to the 10th of an inch. Or not the 10th, the 100th of an inch, like this. And we're still closest to 8.2. In other words, we're in this range. So even though the ranges are centered on the same spot, 8.2, when I have that extra 0 on the end, it's implying that my measuring device is more precise. This is implying that my measuring device has a degree of precision of 0.01 inch, a 100th of an inch, because the last digit in my measurement is in the hundredths place. So that means the error here, the possible error, is plus or minus half of a hundredth is 5/1000ths of an inch, which means we are implying a range of 8.20 minus 5/1000ths, that's 8.195, to 8.20 plus 5/1000ths, 8.205 inches. Notice that is a significantly different range, a much tighter range. When you're writing down a measurement, there's going to be at times that temptation just to drop a 0 at the end of it. But unless you actually measure down to that degree of precision, you cannot put that 0 at the end of the number if it's after the decimal point. So if I report a measurement in decimal units, in decimal inches here, 4.38 inches. In your notes, find for me the degree of precision, possible error, and then that implied range. While we're working on it, I'm going to put a second measurement up there, 0.470. If you get done with the 4.38 inches, do the same for that 0.470 inches. Okay, so for the 4.38, our degree of precision, it's just the place value of that last digit. That is in the hundredths place. So our degree of precision here is 1/100th of an inch, or 0.01 inches. Our possible error, so 1/2 times 0.01. Or you could do 0.5 times 0.01 inches, 0.005 inches, plus or minus, of course. So my range, take my 4.38 minus 0.005. Adding my 0 in there, this is 4.375 inches. To my measurement of 4.38 plus 0.005. Giving me 4.385 inches. So the implied range there is, when I say that that is 4.38 inches, it's implying that that's somewhere between 4.375 and 4.385. The second one here, the 0.470, well, that last digit is in the thousandths place. So the degree of precision there is a thousandth of an inch. The possible error is half that. So 1/2 or 0.5 times 0.001 is plus or minus 0.0005 inches, which gives me a range 0.470 minus 0.40 or 0.0005 is 0.4695 to the 0.470 plus the 0.0005 is 0.4705 inches. There's my implied range. Any questions? This is a conversation I usually dread having because it's a very different thought process. And we're not going to get really technical about it in this course. It's something I want to make you aware of. If any of you were to go on to an advanced degree, a 4-year degree in mechanical design or mechanical engineering or anything like that, even just getting into design, significant digits become an important deal. It's significant digits kind of include what we've just been talking about, but takes it a little bit of a step further. And significant digits are just a way of making sure that when we're doing measurements, that we report measurements and understand those measurements accurately, correctly. So it's basically a standardized set of rules so that this is how you record a measure, how you write it down, so that when somebody else is reading that measurement, they know that if you followed standard procedures, this is what that measurement means when they read it. And for calculating with measurements. If we have measurements that are only measured to the nearest thousandth of an inch, well, we can do calculations and round it off down to a millionth of an inch if we want to, but that's not really an honest report. That's not an accurate report. Because our measurement only went down to a certain size, we can't allow our calculations to get more precise than what our actual measurements were. It's just not possible, and it's not honest as we're reporting it. And so in practicality, it's really not down to that unit, even though we can calculate down to whatever unit we want to. So let's talk about what is a significant digit. Well, a digit is significant. A significant digit is, I shouldn't say important, I should say meaningful to the measurement. In other words, it describes part of the measurement. One of the biggest things we're going to look for is that degree of precision. So a digit is significant if, one, not zero. Any digit that is not zero in a number, in a measurement, is a significant digit. Or a zero if it's between other significant digits. Well, what's that mean? Well, not zero. (241 inches), that has 1, 2, 3 significant digits. (40 inches), that only has 1 significant digit. Because the zero, in that case, does not count as significant. But now down here it says a zero can be significant if it's between other significant digits. 205 inches. The 2 and the 5 are significant because they're not zeros. But that 0 is between other significant digits. It's between the 2 and the 5. So it is significant. That has 3 significant digits. This next one is the part that's tricky. If it is otherwise numerically unnecessary. What does that mean? Numerically unnecessary. Well, that means if it's not needed by the number, then it's significant. The only reason for having it there is because it's part of the measurement. This is tricky because you think, well, significant, that means important. No, they mean two different things. Important means it's needed for the number. If that's the case, then it is not significant. Significant means the only reason for including it is it's part of the measurement. Well, what do I mean by that? Well, (2,800 inches). The 2 and the 8 are significant. The zeros here are not, because they are needed for the number. If I take those zeros out, it changes the meaning of the number. They are important. Not saying they're not important. They're very important, but they're not significant. This has 2 significant digits. This measurement here, 0.00853. The 8, 5, and 3 are significant because they're not zeros. The zeros up here, however, are needed for the number. If I take them out, it changes the meaning of the other digits. They're important again. But again, because they're needed for the number, they're not significant. This has 3 significant digits. .500 inches. That 5 is significant because it's not a zero. These zeros here, if I take them out, they do not change the meaning of the 5. Numerically, they're not important. They're not necessary. If I took them out, the 0.5 still means the same thing numerically. So the only reason to include them is because they're part of the measurement, which means they are significant. So 0.500 has 3 significant digits. One spot where zeros are not needed for the number, so therefore that they must be part of the measurement, is zeros that are at the end of a number and after the decimal. It has to be both. Because up here, these zeros were at the end of the number, but they were not after the decimal. Those were not significant. These zeros were after the decimal, but they were not at the end of the number, so they were not significant. These two were both after the decimal and at the end of the number. So therefore they were significant. So this one here, the 5 is significant. Is the 0 significant? Say no. It's at the end of the number, but it's not after the decimal point. For this number, however, the 0 is significant, or the 5 is significant. What about the zeros? Well, this 0 here is at the end of the number and after the decimal point. It's significant, which means this one is also significant because it's between other significant digits. That number has 3 significant digits. There is a final way that a 0 can be significant. And that is if it is indicated. Well, what do I mean by that? Well, if I have a measurement that comes out to 200 inches, if I just write it like that, this is implying that 2 is my degree of precision. It's implying that it's measured to the nearest 100 inches. In other words, a degree of precision of 100 inches and an error of plus or minus 50 inches, because that is the last digit that is significant. However, if I write it, we can either put the bar above or below the zero, either one. Depending on what textbook you're using, I've seen it done either way. I'm going to put the bar below the zero for this course. What that is saying is that it's indicated that it's measured to the nearest 10 inches. So even though it says, both of them say 200 inches, that little line indicating the zero is saying we really did measure to the nearest 10 inches, but it happened to come out closest to 200. So that zero is still significant. I'm going to have you guys work on some stuff out of your big book here for a few minutes. Page 268, exercise 7-6, problem 7 through 25, the odd. It is also 8:20, so if you want to take a break, let's be back at 8:30. We'll start lecturing from there. So you got the next 10 minutes to take a break. Start on that homework if you like. We'll be back in 10. Starting to get darker out in the mornings. It won't be long before I have to have my lights on in the room throughout all this class. Okay, so it is that time. Let's go ahead and pick up from here. So we're just going to do a quick little review. I'm going to use millimeters for our measuring units here just because it makes more sense with some of the larger numbers. And inches with some of the smaller numbers. So I have 3 examples I put up here. I want you to tell me how many significant digits in each. Let's kind of work through them together here. The 3,050 millimeters. We know the 3 and the 5 are significant. Is this 0 significant? Yes or no?
Yes.
Yes. It's between other significant digits. How about this 0? No. It's necessary for the number, so it's important numerically, but it's not part of the measurement. So 3,050 has 3 significant digits. The 400 millimeters, though, the 4 is significant because it's not a 0. How about this 0 here? It'd be easier. How about I move down to this 0 down here? Is that significant?
Yes.
Yes, it's after the decimal point and at the end of the number. Which means these two have to be significant because it's between other significant digits. That number, 400.0 millimeters, has 4 significant digits. This last one, the 7 and the 2 are significant because they're not zeros. Let's do the easy 0 first. How about this one?
Yes.
Yes, it's between other significant digits. How about this one here on the end? It's at the end of the number and after the decimal point. So yeah, it's significant. How about this one?
No.
No, it's after the decimal point, but it is not at the end of the number. So that is not significant. So this has 4 significant digits. Let's talk a little bit about precision and accuracy. We mentioned precision a little bit as the ability to distinguish between items that are similar. And when we're measuring, that is one of the definitions of precision. Let's think about a target here for a while. If that's the center of my target, If I have 8 holes spaced in blue there, I'm going to do another 8 holes in green. The blue holes are more accurate because they are closer to the desired target. The green are more precise. They are closer to each other. In manufacturing, precision is often associated with repeatability. The first goal of any machine that we set up in a manufacturing setting is to make sure that machine is capable of reproducing a part that's very, 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 very close to the same every time it produces it. That is the precision. That is really a capability of the machine. Accuracy, then, if we have the precision, we have that capability, accuracy is often a matter of simply adjustment. The green holes there are precise, but they're not very accurate. They're not real close to our desired center there. But we can adjust to make them closer. We can fix accuracy with adjustment. Precision we cannot fix with adjustment. Precision is a quality of the machine, a capability of that machine. Well, when it comes to significant digits, precision, just like degree of precision in our measurement, is the place value of the last significant digit. So in a number like 4.23 inches, the accuracy, or sorry, the precision is to the nearest 100th of an inch. That's that place value of the last significant digit. Before, when we did degree of precision, we just said it was the place value of the last digit, but it has to be a significant digit. If I had the number 700 millimeters, the precision here is just to the nearest 100 millimeters, because that 7 is the last significant digit. Accuracy is the number of significant digits. So this one here, 1, 2, 3, is accurate to 3 significant digits. This one's only accurate to 1 significant digit. The theory is that the more every significant digit's getting you closer to your desired target. That one's not quite as easy to reconcile with our common definitions of accuracy as the precision is. So if I'm looking at these two numbers, the most precise number is the 0.035 because that's precise down to the nearest thousandth. This is only precise down to the nearest hundredth. The most accurate is this one. This one's accurate to 3 significant digits. This one's only accurate to 2 significant digits. So why do we care? Well, the answer might be that we don't, but we mentioned early on, not only is this about making sure we write down our measurements in the correct form, it's about calculating with measurements. So when we go to calculate with measured numbers, when we add or subtract, we are all about precision. We conserve precision when we add or subtract. Now, when I say we conserve precision, that means we can only calculate to the least precise number. When we multiply or divide, we preserve accuracy. Well, let's take a look at some examples here to see what we mean. Let's do 4.3 inches plus 2.57 inches. When I add those, 4.3 inches plus 2.57 inches, I get 6.87 inches. However, remember, addition preserves precision. So we look at the precision here. This is precise to the nearest tenth. This one is precise to the nearest hundredth of an inch. Which one is less precise? Well, a tenth of an inch is less precise than a hundredth of an inch. There's more error there. That means my answer has to be rounded to the tenth of an inch. That's going to round 6.9 inches. Well, you might say, well, why would we do that? 6.87 is more precise. It is, but remember, this 4.3 inches here, that's really 4.3 inches plus or minus 0.05 inches, remember? There's that implied error, that possible error in that measurement. When we rounded over here, sure, when we rounded from 6.87 to 6.9, we lost 0.03 of an inch, but our error in that first measurement is bigger than that 0.03 of an inch. We cannot say 6.87 is our result because that's implying, that would imply that this has an error of 5 thousandths, plus or minus 5 thousandths. It does not. The bigger error is this one, that's plus or minus 5 hundredths. So we have to report our answer so that whoever is reading that answer knows that the greatest possible error in any of those measurements used in that calculation was plus or minus 5 hundredths of an inch. So we say we're preserving precision. What we're really doing is reporting the largest possible error in the measurement. Now this can come up with some really weird things, like this. 70 inches minus 2.538 inches. I subtract that 67.462 inches. However, what's the precision of this number here? 10 inches, right? That 0 is not a significant digit. It's not indicated. The precision of this one is to the nearest thousandth of an inch. Well, less precise is 10 inches, which means my answer has to be rounded to the nearest 10. Well, I round that. The 7 says I round that back up to a 70. So here I took 70 inches, I subtracted 2.538 inches from it, and I still have 70 inches. Because in this 70 inches here, there's plus or minus, oops, not 0.5, there's plus or minus 5 inches of potential error. That error is larger than what we're trying to subtract here. Realistically, these two measurements should never be combined because in physics, we would say they're on separate orders of magnitude. That the error in the one measurement, the 70 inches in this case, that error is larger than the other measurement is, so that we really can't combine those. Let's look at multiplication. Let's do 2.4 inches times 0.53. Let's do 0.535 inches. We're going to multiply those. Get 1.284 inches. Inches squared, actually. Now, we said that multiplication preserves accuracy. Remember, accuracy is the number of significant digits. This has 2 significant digits. This has 3 significant digits. The least accurate is the 2 significant digits. That means my answer has to be rounded to 2 significant digits. So I start here 1, 2. I have to round it there. That becomes 1.3 inches squared. It's the same justification that the error in this measurement, as we multiply, is going to be larger than what we just rounded off. It's a little harder to display it than it is. Addition and subtraction is pretty straightforward. You're adding errors that are bigger than the numbers. Multiplication and division, it's a little bit more difficult to show how that error propagates out through. Let's do 4.5 inches times, let's do times 2,800 inches. 4.5 times 2,800 gives us 12,600 inches squared. Now again, This has 2 significant digits. This actually only has 2 significant digits. So we round our answer, starting at the beginning, to 2 significant digits. We're going to round it right there. So this rounds to 12,000 square inches. Division's a little bit trickier. Let's do 0.537 inches divided by 2.4 inches. 0.537 divided by 2.4. First is going to give us it actually comes up better than I thought. 0.22375. Now the inches divide out here. But we still have to round our answer to significant digits. This number has 3 significant digits. This number has 2 significant digits. So we have to round our answer to 2 significant digits. So from the beginning, the 0 is not a significant digit. I don't count that. So I go 1, 2, and I round it there. That'll be 0.22 is what that divides out to be. Let's try something like this. 460 inches minus 59.3 inches. Well, 460 minus 59.3 is 400.7 inches. But how do we have to round this off? Well, we're subtracting here. When we add or subtract, it's precision that we worry about, the place value. This is precise to the nearest 10 inches. This is precise to the nearest tenth of an inch. The lesser precise is the nearest 10 inches. So my answer has to be rounded to the nearest 10 inches. That 0 is in the tens place. The next digit's a 0, so that's going to stay 400. Notice I don't put the 0.0 on the end because that would totally screw this up. However, I can't write it the way I just wrote it either, because that's saying there's only one significant digit. This is only saying the 4 is significant. I have to indicate that 0 is still significant. So I have to put an indicator over that. It says 400, but it's that first 0 is significant. It's part of our measurement because we rounded to the nearest 10 inches. Well, since I only gave you like 30 seconds of work time in the first hour, we'll give you a little bit more work time here right now. Remember from the first hour, it was page 268, exercise 7-6, 7 through 25, the odd, talking about basically significant digits. For right now, then, I'm going to give you page 266, exercise 7-4, 7 through 17, the odd. Talking about your degree of precision and your implied range. Page 269, exercise 7-7, 7 through 21, the odd. I apologize for these pages being kind of a jumbled order here. Page 267, exercise 7-5. 7 through 17, the odd. I didn't write the pages down in the order they appeared in the book. I wrote them down in the order that I was discussing them today, so sorry about that. And finally, page 270, exercise 7-8, 7 through 21, the odd. So I'll let you guys have the last 24 minutes or so to get started on those. I'll be online here to answer any questions you might have.
Big book, right?
Big book, yes.